Hi students, for this first video for online lecture 17, we are now going to talk about two important reaction types. We're going to talk about gravimetric analysis and then finally the acid-base neutralization. So what do we mean by gravimetric analysis? This is going to be taking the precipitation rules that we learned from the solubility rules and putting them to use trying to determine concentration. So the first thing that we want to do is dissolve an unknown substance in water. Then we will react the unknown with a known substance to form a precipitant. This means that we must know the ions that we are using, so that way we can guarantee the formation of our precipitate. This can be done by using a balanced chemical equation. Then we are going to filter and dry our precipitate. We want to isolate our solid and we want it to be as dry as possible. So finally, we are going to weigh the precipitate, and using our chemical formula and the mass of the precipitate, we are able to determine the unknown ion by going and doing our stoichiometry calculations and working backwards. This is a very prototypical lab that you would do in a Chem 119 lab. You are going to take two solutions, form a precipitate, weigh the precipitate, and then see what ions we had in solution. So let's go ahead and take a look at that. So this is an example from the fall of 2017 exam, and we are going to mix excess lead nitrate with 125 milliliters of potassium bromide that has an unknown concentration. When we do this mix, we are going to result with 9.50 grams of lead bromide. We need to determine the concentration of my original KBr solution. So where do I even begin? Let us start with a balanced chemical equation. To do that, we need to have our lead nitrate. So now we need to discuss the solubility rules. Remember that all nitrates are soluble. So this would be an aqueous solute. Then we are going to bring in our KBr, which if we have potassium, that is also going to be soluble. And now we can start to discuss our products. The first product that we are going to form is going to be our lead bromide. Remember that most halogens are soluble, but because of our lead, this is one of the insoluble exceptions. So this is going to form a solid, and the other product that we will form is going to be our potassium nitrate. So now first thing we need to do is look and see if we are balanced. You will notice that I have two nitrates, so that means that I need to have two potassium nitrates, which means that I need to have two potassium bromides in my reactants, and I now have a balanced chemical equation. The last thing that I need to look at is see if my potassium nitrate is soluble. Well, this is very soluble. So remember, because of potassium and nitrate, this is also going to be aqueous. So now that we have a balanced chemical equation, we will see that the only solid that forms is going to be our lead bromide. So let us go ahead and start with that mass and work backwards. I have 9.50 grams of my lead bromide. So where do I go now? Well, I need to go from grams to moles. So what I need to say here is that I have 1 mole of my PbBr2 for the mass of our lead bromide. If I go and put this into the calculator, you will see that I get 367.01 grams of lead bromide for every 1 mole. So now that I have my moles of my lead bromide, I need to go to moles of potassium bromide. So using the balanced chemical equation to go from moles to moles, you will see that I get 2 KBr for every 1 PBr2. So this should give me the number of moles of potassium bromide that I need. That value is going to be 0.0518 moles of my KBr. So now that I have moles, how do I go and get concentration? Well, it's actually very easy. We are going to divide by our volume. So now what I can do is divide by my original volume of my KBR, which is 125 milliliters, but now I need to go to liters, so that way I will have concentration of mole per liter. And if I go and do this math, you will find out that I get a value of 0.414 molar potassium bromide. If I go ahead and look at my answers, you will see that that comes out to answer C. So in this reaction, we are actually using the fundamentals of solid stoichiometry and now working with solution stoichiometry at the end. This is a nice way of tying these two topics together. The second reaction type that we're going to discuss in this video is going to be the acid-base neutralization. In a previous video, we talked about the properties of acids. So now it's time to talk about the property of bases. They have a bitter taste and they feel incredibly slippery. This is why many soaps contain bases. They cause color change in plant dyes, very similar to those of acids, but it is actually a different color and will typically turn it a bluish color of the chlorophyll. Aqueous solutions do conduct electricity because of our OH minus concentration in solution, and we have many examples. Two that you're going to run into all the time in general chemistry are ammonia, which is a weak base, and OH minus, which is going to be one of our strong bases. These are two you should become incredibly familiar with over our course. So now let's look at the definitions of acids and bases. I've talked about the properties, but now we can discuss why they are acids and bases. There are going to be three definitions that we discuss, two of them in General Chemistry 1 and a further one that you will see in General Chemistry 2. The first one that we have is the Arrhenius definition. An Arrhenius acid is a substance that produces H plus or H3O+, our hydronium ion, in water. So as you can see here with our HCl, if we put it into solution, we are going to form H3O+, which is going to be our acid. An Arrhenius base is a substance that produces OH minus in water. So as you see here with ammonia, if I put it in water, I will form NH4+, which is the polyatomic ion, but that is not the part that we are concerned about. We are concerned about forming our OH minus. So the best way of understanding the Arrhenius definition is that we are very product favored and we are very product focused. What are we forming? Are we forming H3O+? That means it's going to be an Arrhenius acid. If I am forming OH minus, that means that it is going to be an Arrhenius base. So for the Arrhenius definition, I want you to focus in on your products. However, that is not our best and easiest definition. The Arrhenius definition works really well in aqueous solutions, so that is why we're able to do that. But not all cases are going to be in an aqueous solution, so we are going to talk now about a better definition, and that is the Bronsted-Lowry definition. A Bronsted-Lowry acid is a proton donor. A Bronsted-Lowry base is a proton acceptor. Notice in this time that we are not going to focus in on the products, but actually the acts of the reactants. So let's take a look at a couple of these examples. So now we have our previous example of our ammonia going and reacting with water, but now you can see that we are going and taking one of the hydrogens from our water, and that is becoming our fourth hydrogen on our ammonium ion. So it is the act of our nitrogen in the ammonia going and taking one of these hydrogens that actually makes this a Bronsted base. If you have a really good base, there's a likelihood that it is going to be applicable to both definitions. So now you can see in this case, we are going to have to label our water as a Bronsted acid. Notice that it is donating a proton. So in the Bronsted-Lowry definition, you are going to see what are known as acid-base pairs. These are going to be species that match up and is going to be the before and after. So our water being the acid, we are going to now label our ammonia as our Bronsted base. Over on the other side, notice that our ammonium that has the proton now has become what is called the conjugate acid. Conjugate meaning what it formed. So now the base has become the acid, and as you can see by our water going and forming OH minus, our acid has become its conjugate base. This is going to be used in great detail when you get to acid-base equilibrium in your General Chemistry 2 course. A Bronsted acid must contain at least one ionizable proton. So this means that not all species that have a hydrogen are going to want to lose their proton. Carbon-hydrogen bonds are not ionizable acid protons. We will see some examples of those as we're going along. Now that we've shown you what the definitions are, we need to talk about how many protons we'll lose. So a monoprotic acid is going to be one in which we lose one of our H pluses. A great example of this is hydrochloric acid that you see here, and notice that it dissociates into H plus and Cl minus. This is a strong electrolyte and is one of my 6 strong acids. If I look at another example, you will now see nitric acid, in which I get H plus and the nitrate anion. This is also a strong electrolyte and a strong acid. But being a monoprotic acid does not guarantee that it is going to be a strong acid. I can also have acetic acid, which we've seen previously, and notice, based off of my double arrow here, that this is at equilibrium. This means that our acetic acid is a weak acid, and that we are going to have competition for the deprotonated form, which you see on the right, and the acid form you see on the left. So this is actually going to be a weak electrolyte. In this video, I'm going to teach you the strong acids that you are expected to know. If you know that it is not one of those strong acids, then it is going to be a weak acid. So then we can go to diprotic acids. These are acids in which we have 2 ionizable protons. A great example of this is sulfuric acid. So if I have H2SO4, I can then dissociate that into H plus and HSO4 1 minus. This is actually a strong electrolyte. So we will consider the first deprotonation a strong acid. But if I go to the second deprotonation, you will notice that I have the double arrow again, and this second deprotonation is actually a weak electrolyte and a weak acid. So this means that when I have H2SO4 in an aqueous solution, we can only guarantee that one of the protons are coming off, but in some cases, some small percentage of the second proton come off. So now, as you are seeing, being a strong electrolyte or a strong acid or a weak electrolyte and a weak acid is not guaranteed based off the number of protons that are going to be removed. The final type of acid type that is very common is the triprotic acid. This means that we are going to have 3 ionizable protons. The best example of this is phosphoric acid. So as you can see here, I have H plus and H2PO4 1 minus. So let's take a look at this balanced chemical equation. Is this a strong acid? Well, the best indicator in here is once again our double arrow, and that shows that this is at equilibrium, and phosphoric acid having 3 ionizable protons is still a weak acid. But now what I can do is go after the second proton, going and forming H plus and HPO4 2 minus. This is going to be a weaker acid. And finally, I can attack the third proton, remove that, and end up with my phosphate polyatomic ion, and this is going to be the weakest acid yet. So as you can see, the mono, di, and triprotic don't tell you anything about the acid strength. It only tells you about the number of ionizable protons that you might be able to go and get. So now what we are going to do is talk about our strong acids and strong bases. The 6 strong acids that are universally believed to dissociate completely are listed here on the left. Those 6 are going to be required for you to know. Those 6 are HClO4, which is perchloric acid, HCl, HBr, HI, HNO3, H2SO4. Those 6 strong acids are non-negotiable and you are expected to know them. Then there is a slight issue, and that is that there are structural analogs or ones that are very close. The structural analogs, which means that they are structurally similar to a strong acid, are very close and then sometimes considered strong acids. Those structural analogs are HBrO4, which is perbromic acid, and HiO4, our periodic acid. These two show up in a lot of literature and are very close to the accepted values for our strong acids. The other one that can get us in a real pickle from time to time, depending on the textbook, is HClO3. This is very close to the same value as H3O+, so some textbooks will consider HClO3 a strong acid, while some will not. This is going to be one of those matters in which, depending on the question or exam, I would notify you in which role it is going to be used. So the 6 in the boxes are non-negotiable. You must know those. Then the 3 on the left, because of their structural analog nature or their close nature in their reactivity, can sometimes be considered, and I want you to know them. On the right side, you'll now see the 6 strong bases. Notice that they are the hydroxides of our alkali metals and our alkaline earth metals. So this is lithium hydroxide, sodium hydroxide, and potassium hydroxide. You will see those in great detail. Calcium hydroxide, strontium hydroxide, and barium hydroxide. Remember that our calcium hydroxide and strontium hydroxide have a solubility issue, so they're not used as much. Another group of strong bases you might run into are the group 1 oxides. So in this case, this would be lithium oxide, sodium oxide, and potassium oxide. These groups are also well-known strong bases, and you will see them used from time to time. If you were to put these species into water, you are going to end up forming OH- and validating the Arrhenius rules. So now there are really 9 that you need to know in each group: the strong acids and the strong bases. The nice part about this is that if it's an acid or a base and it doesn't fall into one of these 9, we can consider them weak acids or weak bases. You will see that the weak acids located down below, we have acetic acid. Notice that you have hydrofluoric acid. So even though it is an acid of a halogen, it is a weak acid. As you come to find out in 120, it is a stronger weak acid, but it does not dissociate completely. So do not include HF as a strong acid. There is our phosphoric acid. You will see sulfurous acid and hypochlorous acid as well. There are a multitude of weak acids, and you will see them more in the next course. For our weak bases, you can now see that you are going to get such things as ammonia, and now you're going to notice a common trend. Many weak bases have a nitrogen that is going to have at some point a lone pair that can go and deprotonate our water or our acid. So weak bases are very important to notice because they contain a nitrogen that has a lone pair. We are going to use them in great detail in General Chemistry 2 and when we get to our organic chemistry courses. So let's go ahead and classify each of the following species in aqueous solution as a Bronsted-Lowry acid or a Bronsted-Lowry base. So let's go ahead and look at species A. This is hydrobromic acid. So this is going to be an acid. We are going to donate that hydrogen in the form of H+. This is also one of our strong acids. So make sure that you are able to identify and label it. Let us go to B. You will notice that this is the nitrite anion. So this is actually the conjugate base of a weak acid. The weak acid that we would normally have is going to be HNO2, which would be nitrous acid, but we have lost its proton. So we don't have an ionizable proton. So this means that our NO2 minus, if we were to put a proton in, would go and form HNO2. Now, we also know that it is an acid for HNO2, so this would be a competition. This means that this is a weak species, but as written, this is going to be a base. So now let's go ahead and look at species C. We have HCO3 1-. So let's go ahead and figure out what would happen if we go and put this in solution. Well, if I were to go and put this into water, it is going to do two things. First off, it might have the basicity or base strength to go and take a proton and go back to H2CO3 and form carbonic acid. In this example, this would be acting as a base. But there is some likelihood that this H could also be deprotonated by water, and you would end up forming H3O plus and the carbonate anion. So now in the second example, this is acting as an acid. What do we call a species that acts both as an acid and a base, depending on the conditions? This is commonly what we call an amphoteric species. Amphoteric meaning that it can act as an acid or base depending on the situation. So in this case, HCO3 1- is considered amphoteric. It can be an acid or base. Another species that lives its characteristics to being amphoteric is going to be water. As you also notice in our upper reaction, if our HCO3 1- is acting as the base, that means that the water has to be an acid. And vice versa when we are dealing with our second reaction. So it's really important that you understand the characteristics of what we are going to do. So finally, let's talk about the neutralization reaction. The neutralization is probably the most important reaction that you will do in the lab, and one that is going to lead us to many important conclusions. Every neutralization reaction has an acid plus a base on the reactant side. You will form a salt and water. So as you can see here with our HCl, that is acting as the acid. Our base is NaOH. The salt that we form is NaCl, and we form our water. We can also go and break this down in an ionic equation. And the nice part about this is that you can see which spectators I have in the sodium and the chloride. And my net ionic equation for most acid-base reactions is going to be H plus OH minus going and forming my water. So what do I have when I have a weak acid? Well, we're still going to form a salt and water, but it is going to dramatically change our net ionic equation. Because my HCN does not completely dissociate, notice that we must go and leave it formally intact in our ionic equation. But because our sodium hydroxide can fully dissociate, it's going to split up into two parts. So now when we get to the other side, we can have our sodium cyanide split up and we will have our water. So now as I cancel out species, I can only cancel out my sodium spectator ion. My cyanide is not a spectator. So now what will happen is that my net ionic equation is going to be slightly different. Notice that you have my HCN still intact, reacting with OH minus, but I am now going to get my cyanide anion and water. This means that the counter ion will show up in our net ionic equation. So let's try a couple of examples. Write the molecular, ionic, and net ionic equations for each of the reactions. So let's go ahead and start with A first. If I have hydrobromic acid, that is going to be HBr going and reacting with barium hydroxide. So that is going to be BaOH2. Our products in this case are going to be BaBr2 and our water. So let us go ahead and check to see if we are balanced. Well, you'll notice that I need to have 2 of my HBRs because I had 2 bromines on the right side, and that is going to lead us to having 2 waters on the right as well. So now we must go and dissociate all species based off of the solubility rules. So here we would have 2 H pluses and 2 Br minuses based off of it being a strong acid. Then for my strong base, I would end up getting Ba2 plus and 2 OH minuses. So now over on our product side, our BaBr2 is a soluble salt. So now I will be able to get 2 plus cation of barium and 2 bromide anions. Our water is going to stay intact because that is now in the liquid form. So I will get 2 H2O liquids. So let us go ahead and cancel out our spectators. That is our barium and our bromide. And you will now see that my net ionic equation is going to be 2 H pluses plus my 2 OH minuses now yield 2 H2O liquids. This is the proof that our HBr is a strong acid. So let's go ahead and try B now. For B, I have sulfuric acid. So that is going to be H2SO4. And I'm going to react it with potassium hydroxide. So we have KOH. If I do this, I should get K2SO4, and I should end up getting H2O. But this is not actually all that correct. What happens in this case is that my potassium hydroxide was only really able to rip off one of my hydrogens. So a better product in this case is going to be our dynamic equilibrium, and we would actually get KHSO4 and only 1 water. So now if we go and use our net ionic equations and try to build this, we would get H plus HSO4 1 minus. Then we would get our potassium and our hydroxide. And now for our products, we would get potassium and our HSO4 1 minus and our high quality H2O. So now what happens in here is that our potassiums are going to cancel. That is the only species that we get canceling. So one thing that we can notice is that I broke this up because it is a strong acid, but our HSO4 is still going to be on that side. So when we do this, we are still able to cancel out here, but when we go to our next reaction, that HSO4 is going to be incredibly important. So for just this half of the reaction, we would end up getting H plus OH minus going and forming our H2O. If we were to continue this further and look at my HSO41 minus, notice that it would not split up and we would have to treat it as a weak acid. So now let's talk about the major acid-base reaction, and that is the titration. In a titration, a solution of accurately known concentration is added gradually to another solution of unknown concentration until we know that the reaction is complete. So what we are looking for is the equivalence point. This is the point in which the reaction is complete. We will use indicators which typically help us with a color change once we are near or very close to the equivalence point. So how this is done in a lab is that we may put a known species in our burette that you will see here, and we will put our unknown in our flask. This means that we can then determine the volume of the known species, and using our simple stoichiometry that we have learned through our past chapters and past videos, we are going to be able to calculate the concentration of our unknown species. So what can we do? Well, we are going to slowly add our known species until we get a color change. Notice that we are getting a faint pink color here in our example. The indicator will dictate what color change you end up getting. So let's try an example of a titration. So how many milliliters of a 0.610 molar sodium hydroxide solution are needed to neutralize our H2SO4? So let us go and write a balanced chemical equation to begin. So we have our sodium hydroxide, and we want to go and completely neutralize our H2SO4. So this means that we want to use it up in its entirety. If I do that, I need to go and form sodium sulfate and our water. So now I need to have two of my bases, and that will form two waters. That stoichiometry is why we cannot use M1V1 equals M2V2 when doing this reaction. Do not ever use our dilution equation of M1V1 equals M2V2 when doing a titration. There is stoichiometry involved, and it could lead to an incorrect answer. So now that I have my balanced chemical equation, I can go and determine the concentration of my species and see if I have that volume. So let us go ahead and get the concentration of the species that I know the most about, that being my acid. So in this case, I have 0.245 molar, but remember that is moles per liter of my acid. So then I need to go and multiply that by the acid volume. So that is going to be 0.020 liters. And this will now give me the moles of my acid that are present. So that is going to be 0.0049 moles of my H2SO4. So now what I need to do is go and get the moles of my NaOH, because that is what I'm trying to determine. So now what we can do is use my balanced chemical equation to say that I would get 2 NaOHs for every 1 H2SO4. So this means that I'm going to need twice as much of my base to do this reaction. If I do that, I will get a value of 0.0098 moles of my NaOH. So as you can see here, I have now calculated my moles of my base. What I can do is divide by the molarity that I am provided with in the question, and this will give me liters of solution. So in this example, I am able to say 0.0098 moles of my NaOH divided by the concentration. So that is going to be 0.610 moles per liter. My moles and moles will cancel. My liters are going to be the denominator of a denominator, which makes it the numerator of my answer. And you would end up with a value of 0.0161 liters. But if we multiply that by 1,000, you would end up with 16.1 milliliters of my base solution. So now you can see the importance of using your balanced chemical equation and then the definitions of your molarity in order to get the liters of solution that you need. Let's go ahead and try one final example for this video. What is the concentration of perchloric acid if the experiment shows that 54.2 milliliters of my perchloric acid neutralize 0.622 grams of potassium hydroxide? So the first thing that I want to do is go and get a balanced chemical equation. So I have HClO4, and I will go and add my potassium hydroxide, and I will end up yielding my water and the salt, which is going to be potassium perchlorate. So now you will notice that this is balanced and that it is stoichiometric at 1-to-1 ratios. So now what I can do is go and start with my mass of my base at 0.622 grams of my potassium hydroxide. I need to go from grams to moles. And I can say that 1 mole of my KOH is divided by 56.11 grams. And just to verify that I have my stoichiometric amount, I can say 1 HClO4 is used for every 1 KOH. If I do that, I end up producing a number of moles of HClO4. If I do that, you will see that that value is 0.0111 moles of my acid. So what can I do now? I am going to divide by the volume of the acid in order to produce the concentration. So I will now divide, make sure that you convert your milliliters to liters. So now my denominator is 0.0542 liters. And what I will now do is have a concentration of my HClO4, which is going to be 0.205 molar HClO4. If I look at my answer choices on the left, you will see that that is going to be answer D. In this video, as long as it might seem, has been 2 very important reaction types. The gravimetric analysis showing us how we can form a solid, and then the second half of the video talking about the acid-base reactions and showing you how important it is that our acids and bases neutralize each other out and that you are able to get your equivalence point. Have a great day.